Hello everyone, thank you for joining this session. I am Valentino Rizzo from Ermes Cybersecurity, and in this talk I'm going to present the work I developed together with Stefano Traverso, also from Ermes Cybersecurity, and Marco Mellia from Politecnico Torino and Ermes Cybersecurity. The paper we wrote is called Unveiling Web Fingerprinting in the Wild via Code Mining and Machine Learning. And in this work, we developed a methodology for automatically detecting fingerprinting scripts and employed it to study web fingerprinting and its adoption in the wild. This work has been funded by the Horizon 2020 Pimp City project. So what is web fingerprinting? As many of you here know, the web is filled with services tracking users during their online browsing activity. These services typically use conventional tracking techniques which exploit client-side storages such as cookies and local storage in order to save uniquely identifying strings generated on the server side to recognize the same user across different websites. These techniques are easily circumventable by users by denying the possibility to store such identifiers to websites or by deleting these identifiers, for example, on the browser closure. Web fingerprinting is a tracking methodology characterized by a completely stateless approach, as it relies on the collection through JavaScript code of device characteristics such as screen size, color depth, installed fonts and plugins, graphic and audio stack characteristics, and many others in order to create a uniquely identifying string which stays the same for the same user as the user visits different websites. This technique is much harder to control by users as there is no trivial way to avoid web fingerprinting without breaking websites. So we considered different fingerprinting techniques in our work. We have browser parameters fingerprinting, plugins and MIME types enumeration, installed fonts enumeration, canvas, audio and WebGL parameters fingerprinting, and hardware information collection. Each of these techniques is characterized by a set of APIs that are needed in order to implement it, and trackers usually combine multiple techniques in order to increase the final entropy of the generated string and, as such, render it more identifying. From the consideration that fingerprinting is then implemented by exploiting multiple combinations of these APIs comes our intuition that machine learning could help us spotting fingerprinting scripts. So we started by developing a static code analysis-based methodology. It starts with the deobfuscation and beautification of the analyzed script. This allows the script to become more human-readable and so to verify the final classification of the methodology, and also to process the script to the static code analysis. Then it proceeds with the creation of an abstract syntax tree representation of the analyzed code. This creates a tree-based representation of the code's syntactical structure. And for example, in the figure, you can see the code section on the left being represented as its tree representation on the right. Then we have the identification in the AST of predefined patterns which could represent fingerprinting behavior. We predefined those patterns based on field knowledge. And finally, we have the script's classification by providing the information we extracted from the tree to random forest and support vector machines as features in input. So we started with a seeding ground truth counting about 300 total scripts. We collected those scripts from Princeton's Web Census database for fingerprinting scripts and obtained non-fingerprinting scripts from websites having a low probability of embedding trackers, such as government and academic websites. We used this initial version of our ground truth in order to train and optimize a preliminary version of our classifier. And we ran this classifier over 100,000 randomly chosen JavaScript scripts. From the results of this classification, we manually verified the labeling for 1800 scripts and appended them to the ground truth, resulting in a final ground truth of about 1900 scripts coming from 752 domains. So we optimized our classifiers and tuned them using grid search and validated their results using k-fold cross-validation. And as you can see from the figure, both classifiers performed quite well with 94% accuracy for both. We can see that we also combined the results of the fingerprinting class from both classifiers, creating their union and intersection, and in particular the union of the result sets on the fingerprinting class, resulting in the higher accuracy with 94.2%, but most importantly the highest recall at 94.4%, which is the measure we were particularly interested into. So from now on, we will call the union of these result sets on the fingerprinting class as the static code analysis results. We then proceeded with the creation of a dynamic code analysis based methodology. We started with the instrumentation of the OpenVPN crawler. We instrumented it to log the executions of APIs which composed the AST patterns we previously mentioned in the static code analysis. Then proceeded with launching the crawler over the Alexa top 1 million websites in order to log the execution of interesting APIs. And finally provided those APIs logs to Random Forest as input features to train the classifier and make it able to recognize fingerprinting scripts. So when comparing dynamic code analysis to the static one, we noticed that it has some advantages, like the ability to inspect runtime values at runtimes and the support for the analysis of obfuscated scripts. But it also presents many disadvantages, such as lower scalability, the need for dependencies for scripts to be successfully executed, the unavailability of the analysis offline, as dependencies often needs to be downloaded, and finally the fact that this analysis does not analyze non-executed code sections. So we proceeded with comparing the dynamic and static code analysis performances. We did so over the set of scripts connected to about 17,000 websites randomly chosen from the Alexa top 1 million rank. And as we can see from the figure, both the methodologies agreed on classifying as Fingerprinters 778 scripts, but then the static code analysis also identified as Fingerprinters 394 scripts, which were identified as non-fingerprinters by the dynamic code analysis, while on the other side, the dynamic analysis labeled 116 scripts as fingerprinters, while the static code analysis missed them. We looked into the causes of those differences and we found that static code analysis missed those scripts where the fingerprinting part was in an obfuscated code section, while the dynamic code analysis missed those fingerprinters that included the fingerprinting section in a code block which was not executed during the particular OpenVPN execution of the scripts. We then proceeded with the characterization of fingerprinters in the wild. We obtained a dataset containing 52 million HTTPS transactions from 982 volunteering users between April and August 2017. This database ended up containing about 400,000 URLs referencing JavaScript files, which once downloaded resulted in about 236,000 unique JavaScript files. Volunteers have mostly been males in the 18 to 31 age range, coming from different parts of Italy. And we also calculated the percentages of Alexa rank websites included in our dataset in order to study how it generalizes, finding that about 70% of websites included in the top 1000 rank are covered by our dataset, about 43% of those included in the top 10,000 rank, and just 17.3% for those included in the top 100,000 rank. So here you can see the results we obtained on this dataset. We ran the static analysis over it, as it was the only analysis which was capable of analyzing this dataset, since it is composed of raw JavaScript files. As you can see, the static analysis concluded that about 1.1% of the scripts which users encountered during their navigation performed fingerprinting activity. We also characterized those scripts by the API that they used to perform fingerprinting, and we found that APIs related to older fingerprinting techniques such as browser parameters, plugins and MIME types, screen, time zone, hardware information and font enumeration were much more common when compared to APIs related to recent fingerprinting techniques such as canvas, audio, and WebGL parameters. We also found that while those APIs are much more common to encounter, obviously, in fingerprinting scripts, the number of scripts that include these APIs, which is reported on the ticks of the bars of the histogram, is much higher for non-fingerprinting scripts. So as non-fingerprinting scripts are frequently using those APIs, automatically detecting the purpose of their usage is not trivial, and from this consideration comes our decision to opt for machine learning to do so. We then proceeded with the creation of what we call the trackers list, which is a list obtained by merging disconnects, easy lists, and easy privacies lists. We used this list in order to find out how many of the scripts we identified as fingerprinters are known to these lists, and we found that less than 40% of the scripts were blocked by those lists, and for what concerns domains servicing those scripts, less than 20% of those domains were included in these lists. We looked into the purposes for which unknown fingerprinters use fingerprinting techniques, and we found that they do so for security and anti-fraud purposes, for bot recognition, but in many cases also for actual tracking. So in those cases, they represent novel trackers which are still unknown to those popular anti-tracking lists. We proceeded with the characterization of known trackers and unknown fingerprinters. For example, in the reported figure, you can see the comparison between the conditional probabilities of encountering an API on the x-axis, once that script included an API on the y-axis. And we can notice that the results are pretty similar between the two categories, with the difference of canvas and WebGL parameters being much more popular in unknown fingerprinters when compared to known fingerprinters. However, from these and other comparisons, we concluded that it is hard to automatically understand the purpose of the usage of fingerprinting techniques, and that differentiating between given families of services is very difficult when basing the differentiation on the set of used APIs. So, concerning the limits of our work, several months have passed between the collection of users' navigation traces and the actual download of the scripts, resulting in about 40% of them being lost as they went offline in the meantime. We recognize the spatial, temporal, and geographical limits of our well dataset, given the demographics characteristics we mentioned before. We are aware that not all fingerprinting techniques have been considered in our work. in fact less popular according to literature. Techniques such as device sensor fingerprinting and battery PI fingerprinting have been excluded from our work. And the in-the-wild characterization has been performed using solely the static code analysis, which is the only one applicable to the wild dataset. However, as we previously mentioned, static and dynamic code analysis are complementary, and only using one of them causes partial result. For this reason, we are aware that the results we presented in our work consist in a lower bound of the actual fingerprinting usage in the wild. So the key findings of our work. We engineered an automatic web fingerprinting detecting methodology which achieves high accuracy in a small amount of time on off-the-shelf hardware. We were the first, to our knowledge, to compare static and dynamic code analysis when studying web fingerprinting, and demonstrated that they are complementary when detecting fingerprinting scripts. We measured the fingerprinting scripts frequency in the wild, finding that 1.1% of the scripts encountered by users perform fingerprinting activities. We characterized fingerprinters and the techniques they adopt. We discovered that most fingerprinting services are not included in popular anti-tracking lists. And finally, we characterized scripts from known and unknown trackers, testifying the variety in the fingerprinting ecosystem. Finally, the methodology we developed in this work is now part of Ermes' commercial product, and we look into improving it in order to being able to differentiate between scripts performing fingerprinting for tracking purposes and those doing so for security or bot recognition or anti-fraud purposes. Thank you for following this talk, and if you have any question, please join the live session.